Hi, my name is Daniil Ravinsky, and this is my 16S rRNA sequence data two-step analysis pipeline for the USeq 16S kit. The first thing we want to do is prep our reads. This will be combined in the first script with de novo assembly of our reads into contigs and BLAST. We will, of course, merge the forward and reverse reads, embed sample names into their read labels, as well as attribute Q-scores. This will be done using the usearch merge function with the default parameters and the relabel option using usearch version 11, which will actually be a piece of software we use throughout. We will strip primer sequences, as primer binding sequences will still be included in our reads and thus have to be removed. We will use fastX truncate for that and strip according to primer length. We will trim our reads globally in a range of 250 to 300, as is typical for Illumina reads. Length trimming is important to help locate unique sequences in the future. And of course, quality filter based on Q-score. Once quality filtering is finished, our filter sequences and reads, our filtered reads are to the side. We will use them further down in this same script and assemble them de novo to contigs using the CLC Genomics workbench with the following parameters that I'm showing here. These can, of course, be tweaked and changed according to needs, and after which we will align this to our local database. Now, the beauty of using BLAST-N and doing alignments is that, especially for 16S now, as of February, NCBI has an rRNA 16S database, which we can also use with our locally curated database to bolster our results. This will be done for contigs with over 1,000 reads using default parameters. After concatenating reads for all samples sequenced in the same run, we can start with our OTU clustering. In this case, I'm using 97% OTU clustering and 100% OTU clustering, also known as denoising. The reason I'm doing this is because contemporary literature finds this to be a better approach. 97% clustering doesn't always differentiate between closely related species, so combining it with denoising is very helpful in the end. On top of it, if there's vast differences between the 97% clustering and the 100% clustering, something's not entirely right. That's just another quality control opportunity in this pipeline, which is great. The next step of this second script is, of course, creating an OTU table using the out tab function and normalizing it by making the number of reads across all OTUs the same. The table gives us a number of reads per OTU, so it's important to normalize, after which we search and filter for our fixed control using the search and filter fix parameters. In the end, we can take our OTUs and taxonomically annotate them to a small classified database, which is either our own or external. It's best not to use large databases due to the fact that they can cause errors. And as a result, we can annotate these then using the syntax command with a cutoff that's according to client demands. We combine it with BLAST-N results to bolster the overall annotation and see if everything mapped. Something may have not mapped, and that's where the BLAST-N result would come in useful. After which we can, of course, visualize it using Chronotools and ultimately, all these three scripts I'm talking about would be ideally combined into one master script, submitted as a job on a high performance cluster. And in the end, after some polishing, this master script would be able to take inputs and give outputs as one concise pipeline. Thank you.